Okay, so I use this PowerPoint in my face-to-face class to go over kinematics in one dimension, which is really Unit 2. So this works just fine to cover some concepts. So things you need to keep in mind for Unit 2, frames of reference and displacement, average velocity, instantaneous velocity, acceleration, motion at constant acceleration. There are problems to solve, and then falling objects. I like to cover it in 1D motion. I think there's kind of a span between Unit 2 and Unit 3 with this, because definitely free fall leads us into projectile motion, which is definitely in Unit 3. So we already know that mechanics is the study of objects in motions. There's two parts to mechanics. We have kinematics and we have dynamics. And right now we're going to look at kinematics. We're looking at how objects move. You have translational motion. There's no rotation at all with that. And then you have rectilinear motion. You still have motion in a straight line path, but you can also have some rotation with it. Okay. Frames of reference, we have to be really careful when we look at frames of reference. All motion is going to be relative, so you need to set your frame of reference whenever you're looking at motion. Typically, the surface of the Earth is set as your stationary frame of reference, but reasons we have to look at frames of reference. Here you see a slide with a person walking through a train car. Now, any person sitting in the train car feels as though they are sitting still, and in reference to the train car, they are remaining still. But if I'm someone on the side of the road looking at the train going by, I see people moving, even though they believe they're sitting still. The person walking through the train feels as though he's moving at just a walking speed compared to the train car. But if we look at his speed compared to the ground outside, the surface of the Earth, he's moving even faster than the train is. So that's where frames of reference can really come into play. And so you have to look at position, distance, speed, acceleration, all of that with frames of reference. Okay? Coordinate axis, same as it is in math class. Okay? Now, we know that displacement and displacement and distance are different. And hopefully you are remembering this as we're talking about it and have been using it correctly all year. Distance is going to be the total path traveled, length, whereas displacement is only the change in position. Displacement is going to be a vector, whereas distance is not a vector. So you can have negative displacement, whereas you will never have negative distance. For displacement, we use x often. Sometimes you'll see r for position, so you'll see delta r for a displacement vector. Sometimes you'll see s. Typically, I like to stick with the x. And again, as I mentioned, displacement is a vector. Vectors have both magnitude and direction, so they can be positive or negative. Scalars are only going to have magnitude. They're always going to be positive. So vector examples that we see here: velocity, acceleration, force, momentum. You know torque now. You know angular momentum. Scalars, speed, temperature, mass, volume, moment of inertia, energy. Those are all going to be scalars. Okay. Average velocity, we're looking at displacement divided by time, so the change in displacement divided by the change in time, whereas average speed is going to be your distance traveled. So speed gives you the scalar, velocity gives you the vector. So you also have to have the vector quantity displacement to get the velocity. And we're looking at a rate. We're looking at how fast. Now these are the formulas for average speed or average velocity. And then we know if you want instantaneous velocity, that's where you have to look at the derivative of the displacement vector. Okay, so just a real simple, quick example. Someone goes for a walk for 70 seconds. and they walk a total distance of 100 meters. So the average speed is going to be 100 meters divided by 70 seconds to yield an average speed of 1.4 meters per second. However, if you look at average velocity, because the person went 70 meters east and then came back 30 meters west, there's only a displacement of 40 meters east. So the average velocity is going to be 40 meters divided by the 70 seconds. Gives you an average velocity of 0.57 meters per second. It's in the positive direction or east. And that gives you your direction there for your vector quantity. Okay? Instantaneous velocity, I mentioned before, is you can't just look at average velocity. You're actually looking at the derivative of the position vector, so the position function. So instantaneous velocity is the derivative of position. Acceleration, we're looking then at the change in velocity with respect to time. So average acceleration is going to be the change in velocity divided by the change in time. How fast are you speeding up, or how fast are you slowing down? So because of that, there are two time units in acceleration. Oftentimes you'll see the units meters per second squared or meters per second per second. You can have meters per second per hour. All of those work. You just have to have two time values. Okay? So if we look here, we have a car that's increasing its speed by 15 kilometers per hour every single second. So at time t equals 0, it has a velocity of 0. 1 second later, its new velocity is 15 kilometers per hour. After another second, it's added another 15 kilometers per hour for a total of 30 kilometers per hour. And if we expand this out all the way to 5 seconds, we now have a velocity of 75 kilometers per hour. Now, realize in between the time 1 and time 2, the car is speeding up the whole way. So there's still an average velocity that occurs over that time span that you could calculate by taking the change in velocity divided by the change in time. And that would get you your acceleration. And if you wanted to find the average velocity, you could just numerically average the two values. Okay? So, acceleration, also being a vector, has direction. You can have acceleration in the positive direction or the negative direction. Also, there's some things to look at. You can have velocity in the positive direction while acceleration is in the negative direction. When acceleration and velocity are in opposite directions, we will often refer to this as deceleration. Okay? When acceleration and velocity are in the same direction, we just say it's acceleration no matter which direction it is. Because you can accelerate in the negative direction while having negative velocity, you would then be speeding up in the negative direction. Okay? So that's exactly, this slide says exactly what I was just saying. And also, if we want to find instantaneous acceleration, we then have to use the derivative of velocity to find the acceleration. That also means that acceleration is the second derivative of displacement. Okay? Now, if we have constant acceleration, we get these nice equations that we can use. I like to refer to them as the magic equations of kinematics. I got that from my own high school physics teacher, so I can't take credit for that. But by rearranging our average acceleration equation, we can actually come up with the one you see here in yellow. That is so useful. And we also can find average velocity by taking a numerical value of two different velocities that we know. And if we rearrange that along with our other average velocity equation of the change in position divided by time, we can get the yellow equation we see here. And so our magic equations of kinematics all fall on this screen. Now, it's really important though, you cannot use these unless acceleration is constant. If you have a changing acceleration, these go out the window, time for calculus. Okay? So, anytime you're going to read a problem, and this is really important in the free response questions for the AP exam, because they work. You have to show your work. Pictures are always important. So read the whole problem, make sure you understand it, then read it again, make sure you really understood it. Decide on what objects you're studying and the time interval, frame of reference. Draw a diagram, draw a picture, always draw a picture, and choose your coordinate axes. Which way is positive? Because if you make to the left positive, which is not necessarily the conventional way, that's fine, but if the readers don't know that, they can't grade you accordingly. So you always want to make sure you mark your axes. Okay, write down your given knowns, write down your unknowns, and that helps you pick what equation to use. Okay, look at your physics that you're applying here. Am I looking at average velocity or instantaneous velocity? Do I have constant acceleration or do I have a changing acceleration? Okay. Another thing that is really important is to realize that you can also divide kinematic problems up into their different time intervals. So let's say you have a constant velocity or a constant acceleration from time t0 to t2, but then from t2 to t3 your acceleration has changed. You can solve this chunk using a constant acceleration, and if this chunk has a constant acceleration but a different one, then you solve a second problem. Okay? So we've got some just very basic examples here where we have x naught equals 0, v naught equals 0. Our total displacement is 150 meters. Acceleration is 2 meters per second squared. We want to know the final velocity. And so this allows us to pick an equation that suits us where we only have one unknown. So we plug in, we solve, and we find our final velocity. Okay? Braking distances, this is another example that would be really important for like car accident investigations, because if you look at skid marks and such, this can be helpful. Okay? So if we're moving at a speed of 14 meters per second for half a second, so the acceleration is 0 if our speed is constant, we've traveled a total distance of 7 meters in that half second. That's usually like a reaction time. From there, hit the brakes. How long is it going to take you to stop? So now you're going to accelerate at -6 meters per second squared. We're going to keep braking until we stop, so final velocity is 0. We know that we already traveled 7 meters, so now how much further are we going to travel for our total distance? And we find that we travel a total distance of 23 meters when we plug in all our values. So that's again where I said you can break it up into different time intervals and carry one answer over into the next part. Okay, I'm going to cover some free fall here, even though it's kind of a Unit 3 thing as well, just to get us started. So gravity. Gravity is a constant acceleration when you're near the surface of the Earth. We know from our planetary motion that as you get further and further away, obviously the acceleration due to gravity changes, but when you're near the surface of the Earth, all objects are going to accelerate at 9.81 meters per second squared. Done. Gravity is an equal opportunity employer, I like to say. It loves you all the same. You're all going to fall down if you try to jump. So that's really useful. The differences that we see and the misconceptions that normally happen is due to air resistance on objects. And hopefully you found that. But in a vacuum, everything, same. Okay? And you can do a demo with this where you've got the ball and a piece of paper and they fall. Well, air resistance comes into play there, and so the paper does this. But if we crumple up the paper and drop it, it's going to fall at the same rate. And I can do that really quickly right here, in case you don't believe the man dropping things. So I've got my lump of paper, got keys, drop, same. Okay, so we want to treat all falling objects the same. Okay, now those magic kinematic equations that we had, we can use all of those and change our x's to y's and change our a to g, and g being 9.8 meters per second squared. We do that, now everything that we were looking at this way goes this way. And since we're near the surface of the Earth, our acceleration is still constant. Okay? So when we look at the 9.8 meters per second squared, that's the magnitude of the vector for acceleration due to gravity. So then we have to decide, okay, which way are we making positive? So typically you make up positive, so then gravity is always negative. Free fall. This is where you only have acceleration due to gravity acting on an object, okay? Even when you throw something upward, and this is like so counterintuitive sometimes for people, but like I'm throwing something upward, right? Throwing it upward. And as it leaves my hand, it's slowing down. It's slowing down. Its velocity is up, but it's being accelerated downward, okay? And so we have deceleration on the way up. And when I hit the very top of my toss, okay, we know that this piece of paper is going to change directions and then start falling down. So since it's going to change direction, it momentarily has to come to a stop. Its velocity is 0 at the top. However, gravity has not turned off. So it still has an acceleration downward of 9.8 meters per second squared. That is almost always a multiple choice question. One of those two. What's the velocity at the top or what's the acceleration at the top? Don't miss it. Okay, so again, velocity and acceleration, not necessarily in the same direction, because here I threw my paper up and gravity's pulling it down, so they're in different directions. Once I hit the top and my paper starts falling back down, now they're in the same direction. They're both downward. Okay, so here are the equations for falling bodies, rearranged. There are magic equations, but now we've replaced x with y and a with g. Okay, and you can take g as positive if you want, and this is the way you do it there. Okay, so here we go. We have a object being dropped from the Leaning Tower of Pisa, just like Galileo did. Okay, so now we're making down positive, so make sure you pay attention to that here. So we've got an object. After 1 second, it's going to be falling at a rate of 9 meters per second squared. 1 second after that, it's gained another 9.8 meters per second in speed. And again, after 3, now we're at 29.4 meters per second. So if we were to do a position versus time graph, each second that it falls, it's going to fall a greater distance. So we're going to have an exponential curve that you see down in the bottom left-hand corner. Okay? And this is what I was talking about when I tossed my paper up. So the ball's released. It's going upward, but acceleration is downward. Therefore, your velocity starts large, gets smaller, 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 smaller. 0 gets bigger, 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 bigger. But the whole way, gravity, same, 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 same. Okay, so quick summary of this. We've got kinematics. We need reference frames. Displacement, change in position. It is a vector. Speed, distance traveled divided by time. Velocity is displacement divided by time. Speed is a scalar. Velocity is a vector. And if you want instantaneous anything, you got to take a derivative. Same thing, acceleration, average, change in velocity divided by time, instantaneous, take the derivative, okay? Your magic equations, only if acceleration is constant, and free fall, acceleration is constant, so you can use them, change your x's to y's and your a to g. Good luck, hope it helped.